want to welcome you to this mini symposium this afternoon. And I want to, thank everyone for coming. And even on this unpleasant day, it seems like winter. Didn't look at the calendar. We're already into spring and still trying to dump some snow or cold rain on us. A few people are still probably on their way, so that's why I started. I waited an extra 10 minutes, but we should start now. So I want to introduce our speaker and the person really behind and responsible for the instrument and the activities of today. So Dr. Hidde Brongersma, I hope I pronounced it close enough, obtained all his degrees in both physics and chemistry from Leiden University, then did a postdoc at Caltech, and afterwards joined the Philips Electronics Corporation in the Netherlands. And that was the early days where he was one of the pioneers of developing the method of low-energy ion scattering that he'll be talking about. During his time in Philips, he directed research on the development of the compact disc, optical fibers, and a variety of high-end glass applications, and received patents in all these areas, as well as the low-energy ion. He has patents also on the low-energy ion scattering spectrometer systems. He subsequently had a joint appointment at Leiden University, and then went over to Eindhoven University in the Netherlands, where he conducted research. He had a very large research effort in the area of catalysis, polymers, 3-5 semiconductors, and ceramics. He's also received a lot of awards, an honorary doctorate, and the prestigious Jacob Kistemaker Prize in Physics. And more recently, he's been involved in further developing and commercializing this new high-sensitivity, low-energy iron spectrometer. And originally, when he was in Eindhoven, it was under the name of Calypso, and now joined with Ion Tough in Germany. And he'll tell us all about the ins and outs of low-energy ion spectroscopy, and as well what's happening today. And he's had, I guess, like 40 years of experience with low-energy ion scattering, being one of the early pioneers, and he's applied it to many, many different areas, and he'll touch base on some of them today. So let's welcome Hidde Brongersma. Thank you.
Yes, thank you very much, Israel, for introducing me, and it's great fun and a pleasure to be here and to talk to you on this low energy ion scattering technique. What I show already in the title, unique opportunities, and that is not only because this technique is special, and I'll show you why it is special, it is also because here on the East Coast in Lehigh you have the machine that can basically do all the things, all the applications that I'll show you that are now possible here. So that is a real unique. Now where is my computer? Okay. The computer is here. Okay, so after introduction, I'll first explain to you, because it's not a very well-known technique, what are the principles and features of this LEIS, LEIS, or whatever you try to call it, low energy ion scattering, how you can analyze the outermost atomic layer. That is where chemistry takes place, that is where catalysis, where adhesion, and a lot of other processes are. So it's very important that you can analyze this outer layer. And at the same time, we are able to do non-destructively in-depth profiling to 10 nanometers. And what is also special and to realize, it's a quantitative technique. So basically, you're counting the number of certain ions, atoms in the outermost atomic layer. And then I'll come to a whole series. I looked at the list of participants, so I try to, well, do a little bit of everything. So just hope that everyone feels a little bit happy with it. Organics, catalyst, ceramics, some goals, and other applications. nowadays in modern society, it's extremely important to have a control at the atomic level. So a quantitative analysis at the atomic level, just for instance this outermost layer, and also in depth, that is crucial to many developers, just to validate whether a procedure really works or not. The simple, how works ion scattering? Well, ion scattering, you come in with noble gas ions, helium, neon, argon, of say a few kiloelectron volts. They scatter from the surface. So it's the same, say, helium ion coming in, it's the same helium coming out, and all we do is measure the energy after scattering. And since this is a billiard ball game, essentially when the particle comes in, it transfers momentum and energy to one of the substrate atoms, and because of that, if it is something very heavy, it will bounce off with almost all its energy, and if it's more comparable, it transfers momentum and it is much slower. So here, for instance, you see a spectrum of a neon ion scattered from an alloy, and it is you start with 3 kilovolts. This is the energy spectrum, and you get peaks for all the elements. Elements that are in the outermost atomic layer. A peak tells you about this outermost layer. Our lateral resolution is not fantastic, so it is not an atom probe where you can look for atoms or nanometers. So we go down to, say, about 10 microns. This is the energy range, and the nice thing about this technique is that in general there are no matrix effects, so there is no influence of the neighboring atoms on the quantification. This is what got us going many years ago, say 92. We have been doing ion scattering, we had developed the technique, and we looked at catalysts, palladium, platinum, nanoclusters on a carbon support, one of these super rough things of 1,000 square meters for only 1 gram of material. And, well, we did see the palladium, we did see the platinum. It's not very convincing, but okay, we were happy with that. But we needed a lot of ions to be able to get that spectrum. Now, the difference between the old days and what's still around in other places in the world and what's new is this one, where you get again this same catalyst. Now you get a nice palladium, you get a nice platinum peak. The statistics is far superior, and at the same time the dose has been reduced tremendously. So while in the past essentially you would kill your catalyst long before you had analyzed it, now you can do it with such low dose that it's essentially non-destructive. What's also good to realize, I give these red arrows. That is where it's a very nice flat background. Why? Because I'm very good at drawing. I made that background myself. Right? Why do I do that? Well, we have the sensitivity not only to see the palladium and the platinum, but of course we also have the sensitivity to see things like promoters. And promoters, this is a commercial catalyst, and I'm not supposed to show what is as promoters in the outermost atomic layer. Also, you should realize that if you compare this with, say, more conventional techniques like XPS, the XPS has all kind of great features, but its sensitivity is significantly less. So you would not see the palladium and the platinum. The loading of palladium and platinum is so low that you don't see it in XPS, but here you see we can do easily a quantitative analysis. What's special about this machine? Well, you have to be very careful with any ion you do on the surface to use as many backscattered ones as you can. So what we do is we come in with ions, they go down, they scatter from the surface, and if they get in between this, well, energy analyzer, double toroidal energy analyzer, you get a dispersion in energy. because there is an electrostatic field, so the fast ones, the high energy ones, are not so much affected by the field than the low ones. So you get an image finally in energy. So instead of scanning through that spectrum and at the same time bombarding the surface and killing the surface, we do now major parts simultaneously. And because of that, we can reduce our primary ion beam, the intensity, quite a bit. At the same time, while you may see the interior, it's a kind of tulip-shaped kind of thing. So it is the full cone. So you come in, and it's the full cone of backscattered particles that we accept. And the analyzer is made for that. So because of that, we are very sensitive. Now I'll go through, just to make you feel comfortable with the properties, I'll go through a couple of features of ion scattering before I get to the application. So some like quantification, sensitivity, things like that. First of all, realize the ion comes in, and this is a cartoon which is time resolved. So I start here in the upper corner, that is where the ion hits. This is simulation kind of thing. You come in with the ion scatters. So the ion is already on the way to the analyzer. You see none of the atoms have moved. The time scale is too fast for that. That only happens later. Then you start the atoms moving, and finally you sputter particles. So it's very important that the first ion gets the surface before any damage, static. If you would do that with a nano cluster on a support, and you hit that nano cluster with a particle, sooner or later you have a chance that that particle will just explode. So you don't want to look after that, but you want to be before. And the feature is of ion scattering, it gets the information before analysis. Now this analyzer is very special because it's so sensitive. So I can reduce my number of ions. So one ion will hit here, another ion somewhere else, and the trick is, statistically, I never come back to the same place. So my analysis is a static analysis of the outermost atomic layer before damage. Quantification, well, there are reports where you can do a review where we went into all the details of it, but I'll just give you a feeling to know what we are talking about. This is just a slide on the absorption of bromine on tungsten. So just a piece of tungsten and some bromine on it. On the left-hand side, here I plot the signal for scattering from bromine, here the signal, from tungsten, and here from bromine. So when I start with the clean surface, it's here, and when I add bromine, signal goes up, tungsten goes down. Now you think that that's trivial. However, realize this is unique. It is only because we are able to look at this outermost atomic layer, and in the outermost layer it is either bromine or it is tungsten. There's nothing else, for the rest it's pure. And since there are no matrix effects, there are no contributions from deeper layers, this is a linear thing. Coverage by tungsten plus coverage by bromine is 1. And that helps enormously to give you a relatively simple interpretation of the spectra. Just one other example. If I take an alloy, like a silver aluminum alloy, what I do is I take a pure piece of aluminum and say, how much aluminum atoms are there in this alloy? Okay, about 34. I do take a piece of silver, normalize my signal, and say, I have 66% of silver. I add that up. Oh, surprise! It adds up to 100. Why? Because at the surface it is either silver or aluminum, nothing else. And that goes through, of course, and that helps you enormously in many things. One other ingredient you know about roughness, if we have, say, very rough materials for catalysis, this is something like silica from 50 to 380 square meters per gram, and as a function of roughness, I plot the oxygen and the silicon signal. And you see there is no real influence. Well, to be really fair with you, if I had taken a pure quartz sample, which is completely ideally flat, I have a little bit more signal. So yes, I have lost, there's only 77% left. I have lost 23%. And we understand quantitatively why that is 23%. So this helps you, so there is not a major structure gap in general if you go from a catalyst to a model system, you can just compare things. If we have organic molecules absorbing on the surface, in ion scattering you will see the top ones, say the green, here the yellowish, they're the backbone of a polymer, while other techniques will probe deeper. You can do imaging. This is an electron microscopy image, but the others are mappings of solder bumps on the surface of titanium. If you see the resolution, the lateral resolution is not fantastic, but it is useful in quite a number of applications. Last ingredient I need is in-depth information. Up to now I've been talking about the outermost atomic layer. And what happens? The helium ions come in, they scatter from the surface, and this is what we've been talking about up to now. But of course a lot of helium ions miss that surface atom, pass along, go deeper, and get scattered in deeper layers. Now, helium is special, it's a noble gas, so it will immediately, when it gets to the surface, pick up an electron, get neutralized. And as I showed you, my analyzer is one for ions, so that means I cannot see them anymore. That is why I may have a very low background. I get a surface peak, but if that helium neutron comes to the surface, and in the last interaction with an atom, for instance with an oxygen atom, in that leaving the surface, there is a quantum mechanical effect which induces a reionization. So you get a certain fraction that makes it even so. So what do I expect as energy spectrum? Well, for this zirconia on silicon, I have a Gaussian peak, which is the surface peak. That is how many zirconium atoms there are in the outermost atomic layer. In addition, I have here a background, a tail as we often call it, and that tells me the depth distribution of my zirconium. What is real life? This is growing these layers with a technique called atomic layer depositions, which is a very careful way in depositing layers. So we grow, and that goes cycle-wise, you put more and more and more of this zirconia on it. And what you see is here in the energy spectrum, well, this is the place of zirconium, this is silica, this is oxygen. After 10 of these cycles, well, you have not a very large peak, but you see some zirconium. Okay, you continue, more cycles, this peak goes up, and look at the red one. 70 cycles. It is still not the maximum. What does it mean? There are pinholes. I mean, if this is real, I mean, we really miss some signal in the zirconium. At the same time, you see, if you are careful, that there is still some silicon left. Yes. So what happens? In the beginning, after cycle, you get some nuclei of zirconium. You add more zirconium. They form islands, they get bigger, and finally you have still a few pinholes left, and finally you get closure. In addition to that peak, here you see, well, already for the red one, this is not a Gaussian shape. You see this tail on the low energy side. That is the depth distribution of zirconium in the deeper layers. It tells you the difference between places where there are still pinholes, and at the same time, at other places, it had been growing already quite a bit. And I put here a scale in nanometers, so you see that for the black one, up to 3 nanometers is the minimum thickness, and the maximum thickness is about 5 or 6 nanometers. Quite a difference of thickness, so quite a thickness distribution. And for microelectronics, that's very important. You try to get ultra-thin layers of just one thickness. And here you see that's clearly not the case. So, peaks I talked about, tails give the deeper layers, the shape gives the in-depth distribution, the intensity depends on which elements are on the surface. So, summarizing, light elements like lithium, beryllium, boron, we are not very sensitive of, say, up to 1% of a monolayer. Fluorine, chlorine, you get better. And then for the heavier elements, say from copper onward to uranium, you get in the range of 10 ppm of a monolayer. That means 10 minus 5 in the outermost atomic layer. Just comparing and contrasting that for a second with other techniques like XPS. If you have an XPS, you may do 1%. If you have a good XPS, you may do 0.1%, but summed over 20 atomic layers. Now I talk about 10 minus 5 in the outermost layer. And that is why, certainly for catalysis, adhesion, and a lot of other applications, this is orders of magnitude, certainly for the heavier ones, more sensitive. So suddenly you start seeing things you could never see before. A tool, what I need in addition, especially if people come from far away, they come with their samples, say, please analyze. And of course, this has been in the air, and depending on air pollution, wherever you come from, that will be dirty. So what we do is we have a plasma source, which, for instance, dissociates oxygen molecules in oxygen atoms. Now, you don't want the plasma on the surface because there will also be ions and it will kill your surface. So what you do is you have a filter here, and that filter only atoms with no kinetic energy can get through. So these are thermal energy oxygen atoms, and they just eat, because of their chemical energy, they just eat away and remove this organic layer. And that is, if you cannot do it in situ, okay, this is one of the tricks to clean your sample afterwards. Now, I come to the applications. I'll do a little bit on organics, just a few things, surface segregation, dendrimers, etc. When you have a polymer, then you should realize that there are two processes related to segregation. One is intermolecular segregation, and that means impurities that come up to the surface. They may be enriched. Well, we have examples where they really go up to huge enrichment at the surface. So you have no clue from the, sometimes you have, but very often you don't have a clue what's really, that elements are certainly in there, but they may come and dominate the surface. In addition, you have intramolecular segregation. That means I have a polymer and there is some functional group that will come to the surface and others will move away. These processes work in real time. So that is, it can be a tenth of a second, it can be a day or a few days. But these are going to influence why all the properties of your polymer after 2 days can be very different from what they were before. So this is one of these examples where you have an ABS, acrylonitrile butadiene styrene polymer, a very common one, and there are stearates of various materials, and basically they are very important at the surface, so adhesion is dominated by that. I have another example in production of OLEDs. When you make OLEDs, you try to get light out of a polymer. So to make an electric contact, you evaporate some metal on it. And in this case, we evaporated barium on top of PPV. And the ideal situation would be the top here, that they're all on top. And then you should get this blue line. Well, you don't. At the moment you evaporate this barium, the barium doesn't like to be at the surface. It has a high surface energy, so it will immediately diffuse in. So what is real life? That's the red one. So yes, you have a surface peak, but you have all this telling you there's a lot of these barium immediately going down into this thing, say down to about 7 nanometers below the interface. We have used ion scattering to optimize these things, get better light output, just change the parameters of the evaporation and everything to get closer to the blue curve. Self-assembled monolayers. Suppose I start with a piece of gold here in green. Okay, you get an energy spectrum. The Gauss peak tells you it is. Yes, it is gold. At the same time, you see here a very narrow background. That is, yes, there's gold in the deeper layers. That is the subsurface information. Now, at the moment I put a nice, well-defined self-assembled monolayer on top, then if there are no pinholes, this gold peak is gone. However, we see if this thin layer, we look at it and we amplify the sensitivity by a factor of 50, you go to the blue one. That is the gold in the deeper layers. The displacement is equivalent to 11 angstroms. If it had been dirty, the layer flat, and then it's red, and we say it's 7 angstroms. We claim that if you add one carbon atom to that layer, we can distinguish it. That is the depth resolution. Last organic thing, plasma oxidation of polyethylene. If you follow the amount of oxygen atoms as function of time, it will fall off. Say, after a few minutes, you see already some oxygen atoms disappearing, and after 2 days, it's gone. In XPS, yes, you integrate over larger depths. So what's happening? Well, these functional groups, so it could be hydroxyl, carboxyl, whatever, they turn away in real time from the surface. They are no longer available for adhesion. They are no longer available for catalysis. So that is why here, after a few minutes, you look only 1 atom deep, you see the first of these hydroxyl and carboxyl groups leaving the surface. Very important for understanding adhesion and how to modify these surfaces that they do have no chance they stay at the surface. Okay, catalysis. Nowadays we have the resolution to look even at platinum gold. I had a little bit on mixed oxides, poisons, nanoparticles, and things like that. This is again a very important application where ion scattering distinguishes itself from all other techniques. We look here, on the one hand, we look for catalytic activity of a number of oxides, and horizontally we plot the ion scattering signal. Now you see if you have a COAl2O4, that's a spinel kind of oxide, then you see that, well, there's not much of cobalt signal. There's not much activity either. If I go to this one with the zinc cobaltate, I have 2 cobalts. Ah, great signal, great activity. And when I go to 3, it's about the same. Why? Well, in these oxides you have 2 different sites where the cation can be. It can be in an octahedral site or a tetrahedral site. The tetrahedral sites are just below the surface. That means, in this case, the first position here in the equation is the tetrahedral site. Cobalt is in the tetrahedral site, so it doesn't do much, and we don't see it. Here, there are 2 in the octahedral site, and there as well. If you integrate over more than 1 atomic layer, just 2 atomic layers the signal, you would not see that. This is typical for looking at the top layer, and then you get this correlation, and otherwise there is no correlation whatsoever between catalysis and what you see. Fuel cells, solid oxide fuel cells. A lot depends on oxygen transport, and there is something always happening at the surface, but no one, not so many persons understand why there is a problem. For a long time one didn't. Here, so these are based on yttria stabilized zirconia. And so if there is yttria or zirconium at the surface, the peak should be here. Well, there are many peaks, but here there's nothing. This means there is not a single yttrium or zirconium atom at the surface. Yes, there is a background that tells you just below the surface, of course, there's lots of yttria and zirconia, but in the top layer, it's missing. What do I see? Well, in this case, it's mainly hafnium oxide, and there is calcium oxide. And depending on the supplier, there can be other elements that go there. But always will there be a monolayer of other oxides, and they are poisons. How do we know they are poisons? Well, if I plot, for instance here, the coverage of calcium oxide against the coverage of yttria and zirconium coverage, the more calcium, the less yttria. But you can also do O16, O18 exchange, and when you do that exchange, you will see that if there is no calcium, you get a very fast exchange of O18 and O16. But at the moment that you complete the layer, which happens easily, you just heat it a little bit and the impurities segregate and cover the surface. Once you have that monolayer, there's no exchange anymore. Calcium is divalent, it will be CaO, and it cannot absorb oxygen, and when you can't do that, you cannot exchange. So it is a poison for this and, say, oxygen membranes and all kind of other things. Right. Coke formation. Coke formation is one of the serious problems in catalysis. In many cases, for instance, this is a 3-way catalyst like you have in your car. It has, amongst others, platinum, rhodium, cerium oxide, ungamma, alumina, and a couple of other elements. Now, after starting your car, it's known that the activity of that catalyst is reduced. Why? Well, we looked here and we saw that in ion scattering you lose also signal of platinum. Now, ion scattering doesn't only say, well, there is coke. It's very easy to detect carbon in such a thing. There's lots of carbon around. What is special about it, you want to know where is the carbon. If the carbon is somewhere on the support, who cares? But if the carbon is on the platinum, that's killer. So, by just looking at the platinum peak, how much that is reduced, we know which fraction of the platinum is covered. And if we don't believe the story, what we do is we take our oxygen atom salts, remove the carbon and say, oops, oh yeah, we get our platinum back again. So it's really covered by carbon. So this is one of the ways how we look at poisons and promoters of catalysts. And of course, applications like a company likes to know how much platinum is available for catalysis. They don't want to pay too much. So you don't pay for so many grams of platinum. You want to pay for how many atoms are there in the outermost layer. So we do that kind of quality control and help people to find out. I'm just jumping from one application to the other just to give a little bit of something maybe for everyone. Nanoclusters, very important. We have been working together with companies like Johnson & Matthey and with Toyota on understanding particle size. And the normal technique you will do is do an electron microscopy. Now, electron microscopy is a super technique. You get a distribution of particle size, you get the size, etc. However, it works very well when these are heavy elements in the cluster and a very low support, say platinum on carbon. Fantastic. It gets a little difficult when the clusters really get small. Then you don't really see them that well in electron microscopy anymore. Another technique is you could do chemisorption, but chemisorption has all kind of other drawbacks, so it's not an easy technique to use. And so we have been using low energy ion scattering to look at what we think about these things. How do we do it? Well, if you have one of these nanoparticles, and I'll show you later, this particle typically for three-way catalyst is 1.6 nanometer diameter, so they are real small particles. We look at the atoms in the outermost atomic layer. If there is segregation, we see it. The signal has to do with how much is exposed. Now this is of course a complicated thing. It's a very rough catalyst, and there are these nanoclusters. On the other hand, if you know how much platinum there is in total, the volume of the platinum, and you know how much platinum there is at the surface, volume divided by surface is a diameter. So based on this, we get an average diameter of these nanoclusters. We do not get a distribution like TM, but we get the average number. Now, and these numbers are for a real typical three-way catalyst. So we do it, and the smaller the clusters get, the more accurate, there's more surface. It's easier for us. So this method is possible essentially wherever TEM fails. So that, like in a real three-way catalyst where you have heavy elements and it's very difficult to get the structures and count these nanoclusters, or when the particles get very small, we do much better. And very often we combine the two things, and if the results agree, we say, yes, one type of particles. Very often they don't agree. We say it's 1 nanometer, they say it's 3, and we say, okay, bimodal distribution. You have big clusters, of course, you see that, but in addition, you have a modal dispersed phase, or very tiny clusters, and you cannot see them, but in catalysis, they're extremely important. So it's very important to compare and contrast these techniques. One of the famous catalysts, copper, zinc oxide, silicas. Just look at the surface, so not in depth, just here. The bulk composition of that catalyst should, say, the zinc to copper ratio should be here. If you do the proper treatment, like the Topsoe company will tell you how to do that, then you go up to here. So an enormous, from here to here, enormous enrichment in zinc. Now the real question is, if you are a chemist, you are not only interested in saying how much copper and how much zinc is there, but what about the valence state? What are the oxidation state? That could be very important. Well, what you do is, well, try XPS. Well, you can't. You would get the valence states, but average over 10 or 20 atomic layers. And the chemistry is really in the top layer. You can do ion scattering. Well, ion scattering gives you the composition, how much copper, how much zinc, but not the ionic, not the valence state. And then there is a third technique, which anyone who has ever done it probably hates. That's chemical titration. You add a molecule like zinc, nitrogen oxide, N2O, and you expose the surface, and the oxygen oxidizes the copper or the zinc, and you see how much oxygen do I use. But you don't use it only for the top layer, but also for the second and the third, so that's not so easy. What we do is we combine these things. And when you do ion scattering plus chemical titration, the ion scattering gives you the composition of the outermost layer. What does the oxygen do? Well, if copper is metallic, it can be oxidized. So then the copper is surrounded by the oxygens and it's shielded. So the signal of the copper goes down by, say, a factor of 3 because of the oxygen atoms surrounding the copper. From that reduction, for every element, for the copper, the zinc, or whatever you would have on your catalyst, that reduction tells you how far was I away from the fully oxidized state of my metal. And that way we determine the oxidation state. So this is an example of a real catalyst where you see low temperatures, small clusters, this distribution, high temperatures, some sintering, and you get there the outermost layer. So you see there's a little bit of copper 1 plus at this temperature, which we think is very important. Last topic, growth. The atomic layer deposition is a technique which is supposed to be extremely accurate. And so I showed you already before the zirconia, and I said, well, you need about 70 or more cycles to actually close the layer. Well, here is a distribution of some examples where we compared ion scattering with what's known, and sometimes it's very good, and after 6 cycles it's closed, and sometimes you need more than 150. So what happens? Well, I explained this nucleation and island growth, etc. And especially in that period, that is not very established. That determines how well you get a conformal, a layer of just one thickness or not. After that, once it's fully covered, then everywhere it goes the same. So that there's no fun anymore. So it's very important to do this transient regime. And so last year, together with companies like IBM and Global Foundries, we collaborated to use our technique to compare and contrast MOCVD, another growth technique, and this ALD for depositing hafnium oxide. And this is part of the results. Here on the left, for the MOCVD, you plot horizontally how much you deposit in total using a technique like RBS, and vertically we say which fraction is covered with ion scattering. Okay, you see here that, well, officially they say around 11. I would say you need about 14 angstroms average thickness, and then you are 100% with this technique. If you go to the other one, you are, well, here either 9 or maybe 10. There's a significant difference between, it may not sound much, but in microelectronics that's very important, that this closure is significantly faster with the ALD technique. And that is why the conclusion was, okay, the origin of the superior quality of these electronic layers for the ALD grown layers, we could show it, and basically there's no other technique that has the depth resolution with which you can do that. I'm coming to my summary. Why do you need low energy ion scattering? Well, you can do it basically for any material as long as you can stick it in vacuum, to be honest. It is a vacuum-based technique. Any temperature. So you can follow at high temperatures things diffusing in or coming out and do that in real time. We can look at the outer layer and we can look in depth. And there are many applications like segregation, anti-wetting, adhesion, grills, pinholes, metal polymer in diffusion, poisons, promoters, whatever in catalysis, nanoclusters. So nanoclusters, it's not only the cluster, but also if it's core shell particles and things like that. Inorganics, I showed you how you do the oxidation state for the top layer and improving cleaning techniques. And to all these sophisticated ones, I have still just one other list just to make you realize that we do all kind of other applications. Say like candy wrappers, especially in the East Bloc, kids like candies wrapped in certain nice, shiny, metallic-like wrappers. We help to optimize them and make them better. Gold mining, FC-16 starfighters, bone tissues, implants, stents, aging of carpeting, anti-wetting for watches, floor wax. And so there's a whole list of, say, what you might call peculiar applications where the outer surface or the near surface plays an important role. And we have been using this technique to solve and help universities, doctors, industries to do that. Well, finally, let me remind you that here you have now a combination of ion scattering. I focused on this one. That is, of course, a very complementary technique. You have both, and you have that, the unique position here at Lehigh. So, thank you very much.
I have some questions regarding the intensities. Going back to the beginning of the talk, you showed this bromine versus tungsten coverage.
Right.
And I noticed that the numbers, the intensities, your counts, at AU, was that in arbitrary units or atomic units?
At AU, it was arbitrary. This is an old slide, so nowadays we give that in counts for number of ions.
Okay.
So nowadays there's an absolute scale, but in the old days it was atomic units.
Okay.
Arbitrary units, sorry.
So now the counts would it really would have a slope of 1. Or that
No,
line would really have a
because the
slope of -1.
sensitivity for bromine and tungsten is not equal. So it depends on how, not all elements have the same sensitivity factor. So you will be more sensitive to tungsten than you are for bromine. So the slope is not 1.
So you've got the calculation.
But it is a well-defined and you calculate that.
And then the other part of the question was, I noticed that in a lot of the peaks, there was a kind of a background underneath it. I noticed it first in the silica you showed for the oxygen peak, as you were adding the zirconia layers on top.
Yeah.
The background around the oxygen didn't really change, and then in many of your other slides as well, you have the nice sharp peaks over the background, and I guess that's coming from the depth now?
Basically, that's the peak. The oxygens also were not changing very much, growing it, because this was from far away, so we oxidized the surface to get rid of the contamination. So it is a monolayer of oxygen, and you have silicons or zirconiums as cation in that matrix. And background, yes, that is just the depth information. So I could in detail explain you why it looks that way. We understand that.
Yeah. I'm Ashraf Khan from Lionel Chemical near Philly. I can also anyway, very interesting talk. I have 2 questions. How does surface contamination affect target peak intensity? And number 2, is specimen preparation critical to your measurement?
Yeah, you could say it's the virtue, the good thing of the technique or your fate that you are extremely surface sensitive. So if there is dirt on the sample, you see the dirt, and you don't see anything else. Now, I showed you for the self-assembled monolayers how when they covered the full thing, the gold pit was gone, and that background had shifted because it was, say, 11 or 12 down. From that shift that you can do for any material, with dirt as well as in this self-assembled monolayers, you can immediately read off and say, okay, I have dirt, it is say 1.3 nanometers. Then you start cleaning, and so this oxygen atom or all kinds of other tricks, and then, whoops, you get the perhaps. But, I mean, you may not like this. On the other hand, that is real life. Your sample is dirty. And if you don't see it on the peak. So it's very important to know about the dirt. When you have techniques that look much deeper, oh yeah, I said it will have carbon, who cares? But if you see that is a monolayer, oops, you have to do something about it.
Please announce yourself. New York, what research?
Nancy Brondberg, BSF Research. Neat talk. Thank you for the talk, Nancy. I'm not getting any sense of how practical this really is, particularly in samples which you would have to clean. Is this something that you could run off, 20 samples a day, or do you need 2 days for one sample? In the real world, this is practical.
Okay. Well, you see this linoleum here, right? We helped our university, they had a problem with the aging of the linoleum. So in one of the buildings, there was linoleum 30 years old. Students would have come over for all these years, and this linoleum should hold 40 years. So they came to us, and we analyzed it. And we found out the reason, and we found a way, Lino wonder how you have to treat the linoleum to get rid of your aging process. So it is definitely practical. So we do those things. And measurement is relatively fast. Say, if you really want to push me, I can do an analysis in 2 minutes. But generally we take maybe 10 or 20 minutes. What takes time is either the cleaning, oxygen atoms, solvents, or other things, or if we look at catalysts, we activate the catalyst just as if it was being used in a real reactor. And how long that takes, whether that is generally not minutes, but that could be many hours in different things, that is determining how fast you are.
Yeah, Peter Zeitler, EDS department. What about isotopes? You've been looking at elemental analysis. What about the mass resolution for it?
The mass resolution depends on the ion you use. In helium, I would say almost any atom in the periodic system looks heavy. So if you want to improve, you go from helium to neon to argon to krypton. So for platinum gold nanoparticles, to know what's in the outermost atomic layer, platinum and gold have isotopes that overlap. So it's very difficult to do, but with krypton 84, we can distinguish the two, and we can quantify with high accuracy what is in the outermost layer of a nanoparticle of platinum gold. So in general, we say, well, isotopes, lighter elements, no problem, but then generally we cannot see single isotopes. So you get a convolution, and from the convolution.
When you do your imaging,
Yes.
are you scanning the ion beam, or is it just...
So you scan basically the ion beam, and at the same time you collect all the information.
And that's how you get in the image the solder particles, the
Yeah, right.
icons. Okay.
Yes.
Couple questions.
Sorry.
There were a couple questions for all the proceeding questions. One is about the contamination. I was just wondering, I see a single layer of water outlet affected. I was So, can you tell us more about the theory how long it take you to spend money?
Well, cleaning, I've been running an application lab because the university wanted me to do that, so we did that. And so for 15 years we run it. And certainly in the first 10 years, statistically, 70% of the samples that came to us were so dirty that people used other techniques, so they never saw it because they averaged over many atomic layers. So you learn well, first of all, you have to identify what's wrong, which is the contamination. Then the next step is, depending on what kind of it is, you have to do some post-treatment to remove that. Or you have to live with it and then realize my catalyst, my oxygen membrane, my polymer, yes, I have that performance because I have 90% of the surface covered by some contamination.
Yeah, especially want to know about water.
Well, water, of course, part of it depends on whether it is, say, chemically absorbed or physical. If it's physical, we might pump it away. If it's chemically absorbed, it stays there, and then it will cover it, and that will definitely shield the underlying material.
How long did you spend to produce an image?
Sorry?
How long did you spend to produce an image?
Oh, depends, of course, how sensitive you have to be, how much time you should spend on pixel. An image is not so fast, maybe 20 minutes or something like that.
I'm a little confused by the image you showed where you had this convoluted picture with nanoparticles in it, and also a slide where you showed surface area and change in constant surface area. But from your initial description, this sounds like a backscattering with must have been a line of sight technique. So I'm trying to understand how you can resolve the surface of nanoparticles that are in this convoluted little cartoon you showed. If the ions coming back have to be a line of sight technique.
Well, first of all, realize we do not look at a single particle. We have a surface where there are many particles, and we integrate because we average the signal over, say, a large area, maybe 1 by 1 millimeter or whatever. If you average the signal, so it's many nanoparticles with you. And only those nanoparticles who are somewhere near the surface, we can see.
So follow-up question then, would this technique not be useful for something like zeolite scientists where you have subtle variations in surface structure and what's on the surface?
Yeah, so certainly in zeolites there's a lot of discussion about what's the outside, because there's a lot of outside surface area in the zeolite. How does that work? We would not be able to see what's in the pores. We can grind it, but that's not a good way to do it. So we could only use our technique to compare and contrast this other technique, what they see, etc. So for zeolites, yes, it's just the outcome. But
is charging an issue in this case?
sorry, charging used to be an issue. Say the last 15 or 20 years, I have not worried about it. The equipment, you just push a button and say insulator, and then the equipment takes care of it. Very careful compensation with few electrons. I mean, we don't have so many ions, so you only need a few electrons at the right place to do the trick. And that does it. We have solved that.
While cleaning with oxygen atom, so if the surface is prone to oxidation, how could we eliminate that?
You mean because you go through air, or? Oh, the all atoms, yeah. So then, yeah, you end up with a fully oxidized surface, right?
Yeah.
Which is not good in that case. So in those cases, just similar to any real life commercial catalyst, we will do the procedure you have to make that surface. So in the pre-chamber, we will have temperatures and gases and whatever to imitate as closely as possible as how one should prepare it, and then go without exposure to air immediately to the analysis.
Okay, so we need to have some background knowledge of the surface, whether it is prone to oxidation or not, this kind of thing.
Yeah.
To know in advance.
Well, otherwise you get it oxidized if you don't say anything. Yeah.
Thank you.
Question. Okay, let's thank you again for